Okay, so let's begin lecture 22, week 8, Monte Carlo simulation applications. This is NE402, intermediate nuclear engineering, diffusion and transport of radiation and Monte Carlo simulation. It's a 15-week full semester course based on 45 lectures, each 40 minutes. And today, we will start with the applications of Monte Carlo simulation. And if we can do it, complete it today, fine. Otherwise, this will continue into the next lecture. So I'll start with modeling bare assemblies. Bare assembly of Godiva and UO2. UO2 is very important for nuclear reactors because it is the fuel of light water reactors. So then I'll model a pressurized water reactor 17 by 17 fuel assembly. And then I'll go through criticality safety. How do we store nuclear material? How do we model it? Then I'll take you briefly through radiation shielding. How do we design a shield around a nuclear system? Because as you've seen in all these lectures, nuclear radiation can be very harmful to humans. And so we require a shield so that we do not exceed the maximum permissible dosage. Otherwise, there can be very bad medical effects, possibly death. Then I'll take you through Monte Carlo perturbation, and end of this series of lecture 22, I'll leave you with a geometry plotting exercise. Now that's my name over here, my cell number, personal email, official email, and personal website. Okay, so let's start with Godiva. Now, as you saw in the previous lectures, Godiva was an experiment carried out at Los Alamos National Labs. And it was a bare sphere of about 94% enriched U235. It had a density of 18.74 grams per cubic centimeter, mass of 52.44 kilograms, and it was critical. So as you can see, this is what the simulation of a sphere gives. So the flux is predominantly fast with an average energy of 1.483 MeV, and you can find the following quantities for an MC simulation, from an MC simulation. How many fissions took place, and how many fissions were caused by neutrons in the range 0.625 eV to 100 keV, and the rest by neutrons 100 keV and above. Now the average fission neutrons you can estimate by this. It comes out to be 2.3261. Is the average fission neutrons produced per neutron absorbed, including capture and fission. While the average number of neutrons produced per fission turns out to be 2.597. Now, if you look at this graph, this is a typical, on the x-axis, you've got the cycle number. On the y-axis, you've got an estimate of K, the system multiplication, using the absorption estimator. And this is the K code data from the run tape file. So what you see over here, you see fluctuations going up and down, up and down, up and down. So this is a typical result which never comes to a point. There's always a fluctuation in this. Okay, now let's try to see what information we can get out of the details of what's happening inside the sphere. So this shows you a picture of the X and Y over here. So on the sphere, you can see now that you've got flux in the Godiva sphere, and here's the legend. So red is maximum and blue is minimum. So you can see that at the center, at the geometric center of the assembly, you've got maximum flux. It's just like in a cup of tea, the hottest temperature would be in the center of the cup. because from the sides there's leakage of heat, and from the surface also heat flows out. So just like that, you can see over here on the z-axis, we've got flux in neutrons per centimeter square per second. Now let's go to a PWR fuel. PWR is a pressurized water reactor, and a typical fuel assembly has 17 by 17 spaces with fuel rods and control rods in it. So, but this is a bare sphere of UO2. It's not, it's not a fuel assembly that I'll show you in a second. But this is a bare sphere of UO2. And this figure over here shows you the K effective. Now, for a 70% enriched sphere of density 10.9, now notice the density has gone down. There it was for Godiva about 18, over 18 grams per cubic centimeter, but now, because it's an oxide, so first metallic fuel used to be used in reactors, and then better fuels which are stronger, they're more, they're stable at higher temperatures. So the oxides, carbides, nitrides. So these are the fuels which had replaced the metallic fuel. So, but as you go into the oxide, the density goes down because there's some oxygen in there. So now it's 10.9 grams per cubic centimeter. This is critical at a radius of 16.3621. Now compare this with Godiva, which was critical at about 8.7 centimeter radius. Here the total weight is 200 kilograms. But you can see over here that again there's fluctuation of K. Okay, so these are the applications of Monte Carlo simulation for a bare sphere. Again, it's very useful to plot fluxes. It may not be able to plot fluxes for a real big system and to understand what's going on. So whenever you start a big nuclear reactor simulation, it's good practice to start small problems with the same material so you get a feel for what answer you would expect. Now again, look at the shape of the flux over here. Again, you see that the red color is in the center, which means that the flux is high at the center, which means that in a nuclear reactor, in the center, there's going to be a lot of heat because this is heat and this needs to be removed. So the fuel rods at the center are exposed to more heat. Now, what does that mean? If you do not remove heat from where it's high, you can end up having an accident. You can end up melting some fuel rod. Now, very few nuclear accidents have taken place in the world. If you look at the history of nuclear reactors, you will find that in recent memory, in the 80s and 90s, you will find Chernobyl blew up, and you'll find TMI, which did not blow up, but which had a minor accident, and of course, Fukushima was caused by the tsunami. So we don't like accidents in nuclear reactors because it can blow up and it can cause a lot of fatalities and it can spoil the environment. So nuclear reactors have got to be safe. So you can see what the flux looks like. Okay, now let's see the flux from the top. So these are contours of the flux. Now you see from here that in a radius of about 16 centimeters, you see where the hot spot is? The hot spot is where the temperatures are highest, over here. So as you go towards the periphery, the temperature falls down. So the danger points are over here. Now, in a nuclear reactor, you always want to know where the danger points are. We call them hot spots. Hotspot is a place where you have a peaking of the flux, which results in a peaking of temperature, which can result in power peaking, which is not desirable. So good practice of operating a nuclear reactor is to have a uniform flux. So we'll see later on in this course that you can achieve uniform flux if you redistribute the fuel in terms of enrichment. So you place variable enrichment fuel. At some place you place 3%, at some place you put 4% enriched. And that's how nuclear engineers like to achieve a uniform fuel burnup. Okay, so this was the section I wanted to show you pictures of the flux. Now this is what we get out of Monte Carlo simulation. Pictures are very telling, and you have seen over here that now you've got a feel for what neutron flux is. Okay, now let's come towards a nuclear reactor. Now, a nuclear reactor has a core which has nuclear fuel in it. It's got uranium or plutonium, and it's got it in the form of cylindrical rods, mostly. They can have any other geometric shape, but there are over 440 nuclear reactors, and most of them are light water reactors, pressurized water reactors, and boiling water reactors. So cylindrical fuel elements about the height of a person, about 6 feet, and about 1 centimeter in dia. So lots and lots of them. In one assembly, you've got 17 by 17 square. And so now we've got to model these. Now they could be in a hexagonal lattice, they could be in a triangular lattice. So let me show you one picture over here. Now this shows you a cylindrical vessel looking from the top, and it's got an hexagonal array of fuel assemblies in the reactor core. So the purple ones are fuel, and the blue ones are the surrounding of the fuel. Okay, and the yellow shows you the coolant or the fluid that is removing the heat out of the nuclear reactor. Okay, so how would you model this kind of a reactor core? Now look at the geometry. They're hexagons, and there's a lattice, which means that if you are able to model one of these, then you can repeat. So that's exactly what we do, that we repeat. So we define one, and then we copy so many patterns until we come to the boundary where you cannot put more. Okay, so MCNP, Monte Carlo, and particle 5B. So I'll take you through a detailed input file at the end of this lecture, but now I'll just say that we define cells by, so first, the first thing we do is that we define a lattice cell. We define universes, and then we're going to place those universes. So let's say that we've got 3 universes based on how many patterns repeat themselves. So if you see that the lattice cell universe 1 is to be filled, if this is defined as cell 1, you can see cell 1. It has no material, it's got a void. So I'll explain all these things. So the material void, and it has a positive sense with respect to surface 21, negative with respect to 22, positive. Now this is that Boolean combinatorial geometry, and fill it with 1. So you can define universes 1, 2, and 4. And you can see over here, I'm going to take you through a hands-on exercise. Right now, just suffice to say that whatever you've got, you define with universes according to that. So in here, let's say we've got the central fuel, which is uranium dioxide. We've got zirconium, which is surrounding the UO2, and we've got water, which is a coolant, which takes the heat away. So we define these universes, then we define a lattice. Now look over here. What do you see? You see lots of 1s, 2s, and 4s. So the boundary, if you count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it's a 19 by 19 square, and the 1 are the universes outside. And because if I want to put 17 by 17, I put some extra ones because it's hexagonal. I'm going to explain that. But 2 is the filler. Then there's 4. There's a different type. This could be a control rod. So you see the 4s and the 2s. Okay, so this is how you define the cells, the surfaces. Remember, these are the mnemonics for a cylinder on the z-axis. That's the radius. So this would be the innermost fuel. So you can imagine from here that the fuel has a diameter of 0.8 centimeter, 0.824. And so the outer radius is 0.57 centimeter. So the diameter is 1.14 centimeter. So this is the outer of the outermost cylinder. These are the various bounding surfaces. As you can see that the bounding surface goes up to 10.8 centimeter. These are all planes, the bounding boxes. Now the source description that we do in MCNP, as I mentioned, these are these volumes, but the source we're going to model with the Watt fission spectrum like this. So all you've got to do in the Monte Carlo code over here is to select your fission spectrum and then to specify the constants which are also inbuilt. So the source definition, you define a source through the source definition card, as we used to call 30, 40 years ago. Now you don't have cards, you've got laptops, you've got soft screens, but historically we had to punch a card. So that's why still in the jargon of preparing computer files, we say card. If you look at any old document, you'll say these are the source cards, these are the surface cards, these are the material cards, these are the tele cards. So this is how you define a source in terms of a source information and a source probability. And you define a source located in a cell if it's a volumetric cell, or you can define it as a distributed source. Okay, so here's a typical source which is defined in cell D1 with distribution 1. So here is the spatial distribution. So this says that if you see how many, there are 1, 2, 3, and 3, 6, and 2, 9. So if I say that my source is distributed in, and these are pointers to a physical cell, that cell 1 inside cell 2 inside 3. So if you, this is how we define the sources, and this is the probability that these are 8 numbers. The number 3 is repeated, is once over here and 7 times repeated. So you've got a total of 8 numbers for these 8 positions. SP2 is a source probability. -3 is the keyword for a Watt spectrum. Okay, now you first need to calculate all your dimensions, and then what you do is that you define your input file, and MCNP runs in 4 overlays, I, P, X, R. Now, input is I, P is to plot, X is the cross sections, and R is the run. So you can, if you don't say anything, it just runs straight away. Now, when you plot that geometry, which I just showed you, this is what you get. When you have a rectangular, when you have a 17 by 17 PWR fuel assembly, this is what you get. So if you count the fuel assemblies, so let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 17 over here. So these are 17 by 17 fuel pins, fuel rods, surrounded by some structural material cladding, and the yellow is the coolant. Now you'll see some boxes which are not filled by the fuel. You'll see, like, here's a box which has a bigger radius filled by something else. Now these are channels which are left inside a core to either control it or for safety, that if you want to immediately shut down a reactor, a shutdown mechanism, you can throw in a very strong absorber. And these are all safety systems and control systems to operate the nuclear reactor nicely. Now, these are the cylinders and the planes used to define this geometry. Now, here's another example where I've got a 3 by 3 assembly. So before you start working with a full PWR 17 by 17, it's a good idea to start small. So what I did when I was a graduate student, I started small, and we used to design something like a 3 by 3 assembly with a central control rod. And if you look at this, then this is where you learn how to prepare your geometry. Now, this is what MCNP gives you when you plot the geometry. It gives you the date you plotted it, the time. So I plotted this in 2013. And this is a PWR fuel assembly benchmark. I did a benchmark, and this is the date. And so these are the basis vectors that I've taken, and the plot I've showed you has its origin at 0.2, and the extent is 3 by 3. So it goes from -3 to +3. Okay, so now these are the various tally cards. So MCNP gives information demanded by the user. Now remember, that's what I told you, that Monte Carlo does not give you a solution everywhere. It gives you a solution where you ask for the solution. So you have to have tally cards, score cards. What do you want to score and where do you want to score? So if you look over here, so, well, here I'm saying that I want the flux. And you can get the volume averaged flux. You can get the current, which means the number of neutrons or photons, if it's a mixed neutron photon problem, the number of neutrons or photons that are crossing a boundary. If you want to know what is the radiation leaving this place, you would want the current. You could want the surface flux. You could want the energy deposition, how much energy is being deposited inside, because it's causing heating up of the thing. So the standard MCNP tallies are F1, F2, F4, F5, F6, and now they've got F8 also. So F1 is current, F2 is surface flux, F4 is cell flux, F5 is energy deposition, F6 is heating. So there's a point detector that's heating, and F8 is a it's a tally to use in a pulse height detector. If you put an asterisk before any of these tallies, then it multiplies by the energy, so it becomes an energy tally. So if you look over here, that if I want, and so for example, if you want a flux, then you'd use F4 or F14 or F24 or F34, any number that ends with a 4. So here I'm using F14. I'm getting the flux in, so I've given 17 entries in the first row of the picture that I showed you for the PWR, then 17, then 14, because maybe I don't want the flux in the remaining 5 channels. So this tells you, again, you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So these are 17 rows and these are 17 entries, except for where I don't have the fuel elements. So this is how you define the address. Cell this, inside cell this, inside cell this, and this element, this row, this column, and this Z. So this is X, Y, Z. And so you can define where you want your tallies. Now, if you want a reaction rate, how many reactions took place? Then remember, a reaction rate means that take the flux and multiply it by the macroscopic cross-section. So the macroscopic cross-section is the microscopic cross-section multiplied by the number density of the material that you are interested in. So any quantity of the form an integral of phi multiplied by the reaction for the M, for material M, integrated over the energy, continuous energy or discrete energy bins, multiplied by some constant. The constant would be the number density. You could even multiply it by the number density and the volume. If you don't want it per cubic centimeter, if you want to know how much MEV is deposited in a fuel element, then you would multiply by the number density and by its volume also. So there are lots and lots of reaction numbers. As you can see that every reaction has an empty number, and you can multiply. I'll just tell you what the multiplier is. So if you want the total number of interactions, the empty number is 1. So there's a long table for this. If you want to know how many elastic scatterings took place, the empty number is 2. For an N2N reaction, it's 16, N3N is 17, and Fx, the multiplication, 18, and NFX, where X can be something else. And the FM, there's an FM number, which is a -6. You could use this alternately. And the 19, 20 is an NNF and N2NF. Okay, then there's a very interesting reaction called the radiative capture. That is N gamma, where the N disappears, the N gets captured, and the gamma comes out. So, for example, for MT18, if you were to use it, then the condition is that if and only if MT equal to 18 is used for fission in the original evaluation. So there are lots of these evaluations, and in some, the total fission cross-section. So it's the total fission cross-section. Otherwise, this is equal to MT18. If MT18 exists, otherwise it's the sum of these four reactions, 19, 20, 21, and 38. So it's the sum of those in which one neutron comes out in a fission, and two neutrons, and so on. Okay, now you can plot using MC plot, and you can use the collision estimator, the absorption estimator, the track length estimator for estimating the system multiplication K factor. And figure of merit, I told you earlier that this is 1 over sigma square, 1 over sigma square T. Sigma square goes as 1 over n, the sample size, and T goes as n. So the time taken is proportional to the number that you sample. The variance is inversely proportional to the number that you sample. So the variance multiplied by the computational time is independent of n, and that settles to a number. It's a measure of your convergence. So here is the collision estimator for flux. So this tells you that it's much higher than 1.4, and here's the FOM, the figure of merit. You can see that the figure of merit for the FOM above, it stabilizes like this. Okay, now I've also used an F-mesh card, shown you the fluxes over here. So you can see that in a 3x3 PWR cell, you can see in the center there's a dip because there was no fuel over there, and the central rod was empty in a 3x3 assembly. So here you can see that the flux is very high at the edges. Okay, now let's come to what are the applications in criticality safety. Now, if you're working at an enrichment plant and you're dealing with uranium hexafluoride, gas centrifuge, then one of the, an important problem could be storage. That as the gas becomes more and more enriched, then you start with, what usually happens is that gas comes in a huge container, and it is just natural uranium in the UF6. But as it spins into the centrifuges, goes through the various cascades, then gradually, by the time it comes out, it has the enrichment that you want. For example, for nuclear reactors, you might want 3%, 4%. For a nuclear weapon, you might want 90%. So if you have a reactor grade fuel or weapons grade, reactor grade UF6 or weapons grade UF6, then storage is very important. Similarly, you might have liquids to store. So how do you store cylinders? How do you store nuclear material in a lab? So these are very important things, because the K, the system multiplication, should never come close to 1. Otherwise, the configuration results in criticality, and it could lead to accidents and could harm the people around the surroundings. Okay, now let's come to radiation shielding. Now, I took you through the basics of radiation and radiation shielding in chapter 1 in one of the earlier lectures. So I think what I'll do is I'll stop over here and we'll continue this lecture from radiation shielding.